So with today, we are done with all the optimal control part, and we start instead talking about reinforcement learning. So just a piece of information, Elisa evaluated all your assignments, and so I'm gonna talk to her later today just to check that the evaluation has gone according to the plan, not too bad. And later this week, we're gonna release, publish the grades, the marks on the website. And pretty soon, ideally within 1 week, we're gonna give you the second assignment on optimal control. So be ready for that. Then we can start talking about reinforcement learning. So reinforcement learning comes from a very different place with respect to optimal control, because while optimal control was born in the control community, as the name suggests, reinforcement learning was instead born in the computer science community. So two very different communities which developed these two theories in parallel without too much exchange between them until recently. But we're going to see that actually they share a lot. They're not the same thing, of course, but they share a lot. They have a lot in common. So in reinforcement learning, what we typically try to do is to find a globally optimal control policy for controlling a dynamical system, which in our case is going to be a robot, but it can be also something else. So similarly to optimal control, also reinforcement learning can be applied to many different fields which are not robotics. Okay, you can apply to control a chemical plant. You can apply to control your portfolio if you're working in economics. And contrary to optimal control, in reinforcement learning, you typically assume that the dynamics is unknown. That's the main difference, which we're going to come back to this point later. In practice, that's often not the case, but at least that was the original idea when this theory was developed, that you have a system you want to control and the dynamics is unknown. In robotics today, very often you use reinforcement learning in simulation. And so actually you do know the dynamics because you have a simulator for simulating your robot. So this assumption is not really holding anymore. And initially reinforcement learning was developed for a system where the state and the control were living in a discrete space. So board games was very often the application where your states can only take a finite number of values and your control inputs called actions can only take a finite number of values. Like think of playing chess. You have a finite number of possible positions of the chessboard, and at each move, you can only move a finite number of pieces in a finite number of ways. So that seems very far from robotics and optimal control, which instead we have seen they work with continuous spaces. The terminology is annoyingly different between optimal control and reinforcement learning. So most concepts we're going to talk about are the same, but almost all of them have a different name, which makes it a bit annoying. But you have to live with that. There's no way around it. I mean, we could pretend it's not there, but then as soon as you go and read a paper about reinforcement learning, you're going to be completely lost if you're not familiar with the vocabulary of reinforcement learning. Another big difference is that in reinforcement learning, people kind of always assume that the dynamics is stochastic. It's not deterministic, which is a bit weird for us because for robots, well, the dynamics is not stochastic. I mean, a robot behaves almost always in the same way. I say almost because there are a few differences, yeah?
Did you upload the file?
Yeah, I just did, but maybe it takes a little while for actually being available for you. So what could be something that changes from one day to the next when you're working with a robot? Yeah, friction could change. Why? Humidity, temperature, that could affect friction. Especially as you use the robot, the motor warms up, and that warms up the whole system. And so friction could actually change because of that heat effect of the motors. That's something that is very real in practice. I've seen that. But apart from these small variations, more or less a robot behaves always in the same way. It's not really a stochastic system. Whereas in reinforcement learning, they were really thinking of working with stochastic systems, especially because I think they were focusing on games. And when you're playing a game, your opponent is unknown. And so you can think of it as something as a stochastic player. Like imagine you're playing rock, paper, scissors with somebody. You don't know if he's going to play rock, paper, or scissors. So you can model that as a stochastic, basically noise that's coming from the environment. You have 1/3, 1/3, and 1/3 probability of your opponent playing rock, paper, or scissors. When I'm going to show you all the equations, actually, I'm going to assume that the dynamics is deterministic just because it simplifies the equation and it doesn't change the core meaning of them. So just to work with a bit of a simpler math, I've decided to get rid of all the stochasticity from the equations, but just know that there is a stochastic version of every equation I'm going to show you, which is fundamentally representing the same concept. It's just a bit longer. And also another difference with respect to optimal control is that typically in reinforcement learning, people work assuming an infinite horizon. Whereas in optimal control, most of the time we have to work with a finite horizon. So here I just reported a summary of the terminology of reinforcement learning, connecting it with the terminology of optimal control. So in case you feel lost at a certain point because you don't understand some terms, you can come back to this slide to see what I mean. So state, luckily, it's still called state. At least that's the one word that doesn't change, but they use a different symbol for it. So in control, people use X. In reinforcement learning, people use S. That comes from the word state, because reinforcement learning was born more in the US, whereas control was born more in Russia. So they use a different letter. The control input is U in control. In reinforcement learning, they call that an action, and they use the symbol A. In optimal control, the system that we are trying to control is called the plant, whereas in reinforcement learning is called the environment. In optimal control, we work with a cost that we want to minimize. In reinforcement learning, instead, we have a more optimistic point of view. We work with a reward that we want to maximize. Of course, the two things are completely equivalent. You just put a minus in front of a cost and it becomes a reward, and the other way around. So you can easily go from one way to the other. You just add in a minus. So the cost to go, it's a concept that we haven't discussed about yet, but it's just the cost basically starting from a given state at a given point in time and moving forward. That's called a return in reinforcement learning. The cost to go of a policy is going to be called value function in reinforcement learning. And this is the most annoying thing of all. The value function in optimal control is going to be called the optimal value function in reinforcement learning. So this is actually very annoying because we have the same term use for two different concepts, which are strictly connected. They are not completely different, but they are a bit different. We're going to come back to these concepts later today, so you don't need to understand them, but just know that there is this possible confusion coming from the use of these two terms to mean two different things in optimal control and reinforcement learning. This is especially dangerous not inside this classroom, where I'm going to make sure that I am clear when using this term about what I really mean. But if you go and read some papers from the literature of optimal control and reinforcement learning, you could find same term, different meaning. So be aware of this. Okay, so moving forward, reinforcement learning is based on a different definition of system dynamics than the one we have been working with, which is Markov Decision Processes, or MDP for short. Maybe you have already seen MDPs in some other classes. Raise your hand if you have. Markov Decision Processes, who knows what they are? Okay, I guess it's the computer science people, right? Okay, they're very common in computer science. I guess if you come more from a mechatronics background, probably you haven't seen them before. No worries, they're not very complex. It's just a different way of representing basically the system dynamics, if especially it is stochastic. So the rest of this lecture is mainly an introduction, a quick introduction to Markov decision processes, so that we have all the terminology and the symbols defined so that we can work then later with reinforcement learning. So Markov decision process is what you use for describing the environment, which is the plant, that's for the system that you want to control. In a Markov decision process, you assume that the state is fully observable, so you have a direct estimate or measurement of the state. In case the state is not fully observable, then you have a so-called POMDP, which is a partially observable Markov decision process. It's a very popular term. And the key property of a Markov decision process is a so-called Markov property, which gives the name to the whole thing, which is that the future is independent of the past if you know the present. That's actually the same property that we always assume in dynamical system modeling. So if you know the current state xt, then the probability of the future state is the same probability that you have, assuming that you know the whole history of past states. So knowing the state before the current one doesn't give you any extra information if you already know the current state. It should be nothing new. And the way you represent the dynamics in a Markov decision process is through this state transition probability, which is the probability of the next state given the current state. And since you assume that the state space is a discrete space, so your state can only assume a finite number of values, then you have a finite number of these probabilities, and you can just build a matrix that contains all these probabilities in its elements. And this is called the state transition matrix. So it's a matrix P that's going to look like this. So every element of the matrix represents the probability of transitioning from a given state to another given state. And if you know all these probabilities, then you know basically the dynamics of your system, which is stochastic, of course. This matrix here has some properties. Each row of the matrix sums to 1. Can you guess why? Yeah, because basically, if you look at all the probabilities in a row, they represent the probabilities of going from state 1 to state 1, then from state 1 to state 2, and so on and so forth until the last one, which is the probability of going from state 1 to state n. And so, of course, the probability of going from state 1 to any state must be 1, because you need to go somewhere after you visited state 1. And the same goes for every row. So all the rows must sum to 1. In case your system is not stochastic, but it's actually deterministic, what's going to happen is that this matrix here is going to be filled with just zeros and ones. You're not going to have any intermediate value, because either you go to a state or you don't go there. There is no probability actually going on if it's deterministic. So we could use MDPs even for a deterministic system. Of course, it feels like an overhead because it's designed for a stochastic system. So you have this typically very large matrix because they're filled not just with zeros and ones. If you have a deterministic systems, there are more compact ways of representing that. So a simpler version of a Markov decision process is a so-called Markov process. So we're going to start from there and then build on top of that until we get to the Markov decision process. A Markov process is represented by a tuple xp, where x is a finite set of states and p is the state transition probability matrix, which we have just described a moment ago. Is also known as a Markov chain. Maybe you have heard that. And here we have a little toy example of this. It's a Markov chain containing only 3 states. We have state study, state break, and state home. And these arrows represent the possible transitions from one state to another. And the value that you see on top of the arrows represents the probability of that transition happening. So if you're in state study, for instance, you have a probability 0.6 of remaining in that state. You have a probability 0.2 of switching to the state home, and another probability 0.2 of moving to the state break. And of course, if you take the sum, 0.6, 0.2, 0.2, gives you 1. We can see the same information here in the first row of the probability transition matrix. So this matrix now is a 3 by 3 matrix because we have 3 states. The first row corresponds to the starting state study. This is a starting state break, and this is a starting state home. And the column corresponds to the next state being study, break, or home. So here we have probability of remaining in the state study. Here we have the probability of remaining in the state break. And here we have the probability of remaining in the state home. So in the diagonal, we have the probability of remaining in a given state. And then in the off diagonal, instead, you have the probabilities of transitioning to a different state. So in this case, this one is going from study to break. So it's this. And you can check all the rows, they sum up to 1. So 7 plus 2 plus 1 is 10, and 2 plus 8 is 10. Here we have 0 because there is no arrow going from home to break. Supposedly, when you come to the university after you were at home, you don't start your day with a break. You start with studying and then you take a break later on. Makes sense. Even though I do start with a break when I come here. I should update the slide. Okay, the state transition probability matrix, it's a very important component of an MDP because it has some mathematical properties that are very useful for deriving reinforcement learning methods. In particular, since the matrix has all non-negative entries and it is irreducible, which we're going to talk later what it means, by the Perron-Frobenius theorem, we know that it has the following properties. So the main one is that the largest eigenvalue in norm satisfies these inequalities. So it's bounded below and above by these two quantities here, which are both 1 for this specific state transition probability matrix, which means that the largest eigenvalue is 1, always. Doesn't matter which Markov decision process you're working with, that matrix has the largest eigenvalue equal to 1. And if the largest is equal to 1, well, all the others are, of course, smaller than 1. And that's a very important property because what it means is that if you take that matrix and you multiply it times a vector, then the norm of the result cannot be greater than the norm of the original vector. Because the eigenvalue represents how much the matrix is amplifying in a multiplication, a vector. And so if the largest eigenvalue is 1, there is no amplification. It can only restrict, can only contract the vector you're multiplying. And this property is at the core of all the convergence proofs of reinforcement learning algorithms. So it's very important to know it. It's very hard to understand where it comes from, but once you accept this property, then all the proofs become relatively simple. So just to connect this with what we have been seeing so far in terms of representing the dynamics of the system, in optimal control, the dynamics, we have typically represented it with a function f. In this case, it would be discrete time dynamics. So the function f of x gives us the next state x plus. Typically, we were writing it as x k plus 1 equal f of xk, but it's the same thing, just a different notation. In Markov processes, instead, the dynamics is encoded as a probability density function. So for each pair of states, we have this probability of transitioning from state x to the next state x plus. So of course, this is a more general way of representing the dynamics because it can be stochastic. If it's deterministic, then, well, these probabilities are going to be either 0 or 1. In this way, we cannot have stochasticity. I mean, this is a deterministic dynamics. However, there is a branch of optimal control theory that deals with stochastic systems. You can have like stochastic optimal control, even though we haven't discussed about it. And in that case, what you would do is that you add another input to your dynamics function, typically called W, which is an uncertainty. And you say that W is an uncertain parameter which follows a certain probability distribution. Typically, this probability distribution is known if you're doing stochastic optimal control. It can be a Gaussian or it can be a uniform probability, whatever. And this parameter can represent like actuator noise, sensor noise, dynamic uncertainties, external disturbances. It can represent everything that you want to model as something that you don't know exactly. So this would be like the corresponding way of modeling stochasticity in control theory, as opposed to the way of modeling stochasticity in reinforcement learning. And the main difference is that this one works well for when you have a continuous state space and control space, whereas this one works only if you have a discrete state space, because you need to have a finite number of possible states, which of course doesn't work well with robots which have a continuous state space. But that's how reinforcement learning was developed, basically. So while reinforcement learning typically uses this way of modeling things, whenever possible, since pretty soon I'm going to switch to a deterministic setting, even when talking about reinforcement learning, I'm going to use this way of representing the dynamics whenever it's possible, because I find it's more suitable for our application of robotics. But in many cases, you can use either. So it's a matter of choice. Just keep in mind, these are kind of interchangeable up to certain limits, of course, which we just discussed. So we went through the Markov chain. Now we can introduce an extension of it, which is the Markov Reward Process. A Markov Reward Process is just a Markov chain where you add the concept of a cost. Actually, it would be a reward in the original definition, because it's a Markov Reward Process, not a Markov cost process. But since we are used to working with the cost, I try to stick to that. So a Markov Reward Process is defined by this tuple. So we have the state space X, the transition probability matrix P, which we already know. But then we also have a cost function C and a discount factor gamma. So the cost function, we already know what it is. The only difference with respect to the classic like optimal control definition of the cost function is that here we need to define it as an expectation, because since the dynamics is stochastic, we don't know what the next state is going to be. So when evaluating the cost, we need to take the expectation of the cost, because the state is a random variable. So the only way to evaluate it is to take the expectation. Well, it's not the only way, but it's the easiest way to evaluate it. Otherwise, it's just a random variable, so you can just, it's not a value, it's a PDF. And then we also introduce the discount factor, which is a very important element in reinforcement learning. It's a scalar value between 0 and 1, which is part of the problem definition. So it's typically up to the user to define it. And it basically discounts the cost in the future. And this is because in reinforcement learning, we typically work with an infinite horizon. And working with an infinite horizon, we need to be very careful not to have an infinite cost, since we are summing terms up to infinity. Well, if these terms don't go to 0, then the summation is going to diverge to infinity. And the discount factor is mainly there to prevent that from happening. I'm going to be more precise in a moment. Let me just first describe this extended version of the example we have seen before. So it's the same Markov chain we have seen before, but we just added the cost to each state. So every state has a cost. The cost for going home is very high, is 3. The cost for taking a break is softer, is 1. And the cost for studying is actually a negative cost, so it's a reward, and it's -1. So you get rewarded if you keep studying, you pay a little cost if you take a break, and you pay a high cost if you go home. Let's be a bit more precise now about what I meant with the discount factor. So in reinforcement learning, the cost function that you want to minimize is not simply the summation of the running cost, but is a discounted summation of the running cost, which means that the current cost at the current time step is considered as it is, but the cost one time step in the future is discounted by the discount factor. So it's pre-multiplied by this value which is between 0 and 1. So, and it has to be smaller than 1 and also bigger than 0, otherwise you're not considering the future at all. And so this value makes so that paying a cost in the future, it actually costs a bit less than paying the same cost now. So it's better to pay a cost in the future than to pay a cost now. And by how much that is better, well, it depends on this value gamma. So as gamma tends to 1, then the future and the present gets closer and closer in terms of cost. And instead, as gamma gets closer to 0, then you're going to be more and more myopic in your choices. So you're going to prefer to postpone payment to the future rather than to the present. So it changes really the behavior of the policies that you're trying to optimize. And as you move forward in the future, the discount becomes stronger and stronger because you're taking the power of this value between 0 and 1. So it's going to become closer and closer to 0 as this power gets higher. So after a certain number of steps, which how many depends on the value of gamma, but doesn't matter which value of gamma that you use as long as it's between 0 and 1. After a certain number of steps, gamma to the power of k is going to be very close to 0, which means that whatever happens from that point forward, it has almost no effect on your choices right now. So you're kind of almost cutting your horizon at a certain point into the future. It's not a hard cut, it's a smooth cut, but it has this kind of effect of stopping your worrisome about the future at a certain point. So when you set gamma very close to 0, you can expect your policy to have a very myopic behavior. So to do whatever it can to get low costs now, doesn't matter if that means paying a high cost in the future. So that's not good. You typically don't want a myopic policy. You want a policy that can take the future into account. It's a bit like having an MPC with a very short horizon. It's going to be myopic, so not going to work well. If instead you set gamma closer to 1, you're going to have a far-sighted policy which looks way into the future. but that typically is going to be paid in terms of convergence speed of the algorithm. So the higher gamma, the slower the algorithm is going to be to converge. It makes sense. You're paying for being farsighted. And there are different reasons why it makes sense to introduce discounting, especially when you're working with an infinite horizon. The main one I already told you is to avoid having an infinite cost. Because just because we have introduced a discount factor that is actually should be strictly between 0 and 1 to make sense. If your running cost is finite, which, well, typically that's the case, then this summation converges somewhere. It doesn't diverge to infinity. So that's a very nice property. And also another good reason for introducing discounting is that since we have an uncertain dynamical system because we have a stochasticity, then the future is uncertain. And so it makes sense to give higher priority to the cost you're paying now than to the cost that you're going to pay in the future, because you cannot be sure that you're going to be paying that cost because, well, there is uncertainty in the dynamics. So the discounts also represent that. And also, if you think of it in terms of like economics, it's better to pay a cost in the future than to pay it now. Because if you're not paying it now, then you could invest that money, get an interest rate on that, and then when you're paying in the future, you have a bit more money to use. So it makes sense even if you think of it in terms of economics. Well, your cost not always represent a real cost in terms of money that you have to pay, but sometimes it does. So now that you have introduced the cost function and the discount factor, we can also introduce the cost to go, which is called the value function in reinforcement learning. It's a very simple concept. It's just the costs that you pay starting from a given state. And, well, in this case, you have a Markov reward process, and so you just follow the dynamics of the process. So V of X is simply the cost starting from the state X and letting the dynamic go. It's of course an expectation because the dynamics is uncertain, so you don't know exactly where you're gonna land, but in expectation you can evaluate that cost. And if you want, you can represent this in a recursive way by saying that the value function for the state X is the current cost that you pay at the state X plus the discount factor times the value function for the next state, f of X. Let me erase this one because it doesn't apply. So I don't know if it's clear where this comes from. I guess not. So let me make it a bit more clear. So I just unrolled the definition of the cost, of the discounted cost. There is the cost at the current time t plus the cost at the next time discounted by gamma plus the cost at time t plus 2 discounted by gamma square, and so on and so forth until infinity. And you can rewrite this as LT plus gamma times LT plus 1 plus gamma LT plus 2, and so on and so forth. I've just collected gamma in front of all the terms after the first one. And then this thing here that we have in brackets, well, that's just the value function starting from the next state. So this is just v of f of x, or v of x t plus 1. Now, all the math I've done here is for the deterministic case. You could do the same for the stochastic case. You just have a bunch of expectations in front of all the terms, which is just making the math longer without changing the concept. So that's why I prefer to do the math in the deterministic case. It's just shorter. So this expression here, which represents the value function in terms of the value function, so it's a recursive definition of the value function, is super important. It's super important. It's at the base of all reinforcement learning. And it has a name. It's called the Bellman equation. This is actually also at the base of dynamic programming, which is going to be the next topic. So this Bellman equation we are seeing here in like function form, but since in reinforcement learning we are assuming that the state space is discrete, so we have a finite number of possible states, we can also represent it in matrix form, because we're going to have a finite number of possible states, and so we can represent V as a vector, because we can have one value for each state. So we have a finite number of values that the value function can take. Same thing for the cost function. We have a finite number of values that the cost can take, one for each state. And so V is a vector, C is a vector, gamma is a scalar. And then here we have the value of the next state. Now, since my dynamics is represented as a state probability transition matrix P, the value of the next state in expectation can be computed by multiplying this probability matrix P times the vector of the value function. Because if you think about what this multiplication does, I mean, we can see it here. Let's take the first row. Here we have the probability of transitioning from state 1 to state 1, from state 1 to state 2, from state 1 to state 3, and so on and so forth. So when we do this multiplication, we are basically multiplying the first row times this vector. So we are taking the probability of going from state 1 to state 1 times the value of state 1 plus probability of going from state 1 to state 2 times the value of state 2, and so on and so forth. So what are we computing actually? Yeah, we are computing the expected value. It's not cost, it's the value at the next time step if we are in state 1 now. So if you're in state 1, you have a certain probability of transitioning to any other state in your state space. And you're taking basically a weighted average of the values of all the states, whereas the weight is the probability of transitioning there. So that's exactly the definition of the expectation. It's a weighted average on expectation, whereas the weight is the probability of that specific event happening. If we were in continuous space, it would be an integral, but luckily we are in discrete space, so it's just a summation, which is easier. If your dynamics is deterministic, then we know that this row is actually going to have all the elements at 0 except one element, which is going to be 1. And that element tells me what is going to be my next state, which is deterministic. And so in that case, it's going to act as a selector, and it's going to simply select the value of the next deterministic state. But in the general setting, it's stochastic, so we need to do this multiplication to do the weighted average so that we get the expectation for the value of the next state. Okay. So this is just a way of rewriting this expression here, but this expression was for the deterministic case. This one is for the stochastic case, and it's in matrix form. And it's very useful that it's in matrix form, because then we can talk about solving this expression for the value function, so computing the value function. How would you solve this expression?
Need to invert the matrix B.
Well, if I multiply times P inverse, I get P inverse V equals C plus gamma V. So I haven't solved it.
E power minus 1 before the C.
Yeah. Forgot that.
Calculate minus gamma times PV, and then you have the identity matrix plus gamma times B times V.
Yeah.
You realize that you have T, and then you just need to invert I plus gamma P, and then you have V equal to C times, no, V equal to.
So you can just move all the terms containing V to one side, and then what you get is identity minus gamma P times V equals C. Well, this is a linear system of equations. So yeah, you just solve it. So that's exactly the solution that I reported here. V is equal to the identity minus gamma P inverse times C. So you can compute the value function by solving a linear system of equations. The problem in practice is that this is not typically how we do it, because the size of this linear system of equation tends to be pretty large for interesting cases. So you can do that if you're working with a small MDP, maybe a few hundreds or thousands of states. But if you're working with a large MDP, which has like million states, then inverting a matrix of 1,000,000 times 1,000,000 entries is not something you can do. And so in that case, there are actually iterative methods for computing V, which are a way of approximating the solution of this linear system of equations. So these iterative methods are going to be the subject of the next lecture. But just, I think it's important to know that what you're actually doing when you're trying to compute the value function is simply like solving a linear system of equations under the hood. It's just too big for you to solve directly. And now we can get to our final target, which was the Markov decision process. So the main difference, the only difference between the Markov reward process and the Markov decision process is that now we're going to introduce control. So in the Markov reward process, we didn't have control. We just had states, probabilities of transitioning from one state to another, and we had a cost associated to each state and a discount factor, but there was no control input. The system was autonomous. In a Markov decision process, the keyword to focus on is decision. There are decisions to be taken. And those decisions are taken through the control inputs or the actions, as we should call them in reinforcement learning. So this is a tuple that's defining an MDP, and that's the same tuple we had before. We are just adding the space of the control inputs U. So even this space here is supposed to be finite in Markov decision processes. We have a finite number of possible actions that we can take. And now the probability transition matrix actually depends also on the control inputs U, which makes sense. Also, the cost in general depends also on the control inputs. Doesn't depend only on the state. And now we are recovering something that looks much more similar to the setting of optimal control we have been working with so far. So now that we have the concept of action, we can also introduce the concept of a policy. A policy is something that we would call a controller in control theory. It's just a mapping from state to actions. And in general, it can be stochastic, this mapping. So even the policy can be represented as a probability. So given you are in state X, then you have a certain probability of taking the action 1, another probability of taking the action 2, another probability of taking the action 3. Again, this makes a lot of sense if you're working with a stochastic system. Like think of playing games. If you're playing rock, paper, scissors, of course, the best thing to do cannot be deterministic. Otherwise, your opponent could exploit that. If you're always playing rock, well, your opponent is going to always play paper and beat you every time. The optimal policy in rock, paper, scissors is to play rock, paper, scissors with a probability of 1/3, 1/3, 1/3. So your policy needs to be stochastic. In robotics, that's less obvious that it makes sense to be stochastic in the policy. And indeed, very often the final policy that we want to achieve is a deterministic one. But it could still make sense to use a stochastic policy just for the policy search process. So maybe at the end you converge to a deterministic policy, but while you're optimizing your policy, maybe you want to keep it stochastic, because stochastic policies are better at exploring the range of all possible actions. And they also provide some smoothing effects over the value function that may be useful for problems where you have non-smooth dynamics. So we are still gonna sometimes retain these stochastic policies, even if in the end we don't want it.
Sorry.
Yeah.
Please repeat what is the policy, the meaning of the policy.
Policy is a controller. It's a function that maps the state to the control. So it can be a direct function like this, if it's deterministic. So u is a function pi of x. Or it can be a stochastic policy, and in that case, it's going to be represented by a probability density function. So for every pair xu, you're going to have a certain probability. So for the rest of the course, we are going to work almost entirely with deterministic policies. But just so you know, there are RL methods that work with a stochastic policy for the reasons I said before. Another very common tool in reinforcement learning is the action value function, which is an extension of the value function, which takes as input also the action. So the value function was the cost starting from a given state. Now, the action value function is the cost that you're going to pay starting from a given state and then applying a given action. So it's a function of two things, the state and the action. That's why it's called the action value function. It's basically an extension of the value function that takes as input also the action. Now, when defining the value function and the action value function for a Markov decision process, we need also to be a bit more precise by what we mean when we say the cost starting from a given state, because now the system is no longer autonomous. So starting from a given state, you don't know what is going to be the future cost, because that depends on the actions that you decide to take. Like imagine you're driving a car, you're starting from a given state, so the car is in a given position. That doesn't tell you anything about what's going to happen in the future, because the car is driven by a human being. So you need to know what is the human being doing to evaluate what is the future trajectory of the car, and so the future cost. So now for a Markov decision process, the value function and the action value function are going to be associated to a policy, because it's only if we have a policy that is defined that we can talk about the expected future cost. So the definition of an action value function is the following one. It's the cost starting from a state x, applying the input u at the first time step, and then afterwards you follow the policy pi. So the action value function is actually a function of three objects. It's a function of the state, the action, and the policy. And note that this action and this policy could be completely independent. So the action does not need to be coming from that policy. It can be a different action. So that's how we write it. It's basically the cost to go, assuming that the current state is x, the current control is u, and the controls for every time step after this one follows the distribution pi, where pi is the policy. So even with the action value function, we can write it down in a similar way that we saw for the value function. So for the value function, we had the Bellman equation, which allowed us to write the value as a function of the value. Here, we can do the same for the action value. We can write the action value as the current cost for the current state and control plus discount factor gamma times the action value function of the same policy pi, but computed at the next state and for the action given by pi evaluated at the next state. It's almost the same structure as the Bellman equations that we saw before. We are just replacing basically V with Q. And this guy here, the Q function for the next state and using the policy pi as action, you can also write it as simply the value function for the next state. Because since this action and this policy are the same, so the action is coming from the policy, then this is actually just a value function because we have this property here. That's the relationship between the value function and the action value function. If you take the action value function and you evaluate it for the action that is given by the policy, then this is the same thing as the value function. Because the value function is assuming that all the actions are taken by the policy. Instead, the action value function assumes that the first action can be different. But if the first action, you assume that it's the same one that the policy would choose, then they're all the same. They're all coming from the same policy pi. And so that's basically what the value function is computing. I don't know if that's clear. Want me to repeat? So the difference between the value function and the action value function is that in the value function, you're assuming that all the actions are coming from the policy pi. So V pi of x is the cost that you pay starting from state x and using policy pi for all the actions. The only difference here with the action value function is that you assume that you start from state x, you assume that all the actions are coming from policy pi except the first one. The first one is specified as an input. But if the first action is also coming from the policy pi, then you go back to what the value function is computing. And so these two things are the same. Only for this special case where the action is coming from pi. If here I had something different from pi of x, then this equality wouldn't hold. Okay, we are almost to the end. There is just one extra concept, which is the optimal value function. It's a very simple thing. We have infinitely many policies that we can work with. Out of those policies, there is one that is optimal. It's the policy that is minimizing my my return. So the summation of the discounted cost. So if I use the optimal policy, then I have the optimal value function, which is the minimum of all possible value functions over all possible policies pi. And we're going to represent that with a star on top. So V star is the optimal value function. So it's a minimum of all the value functions. Similarly, you can do the same for the action value function. it's the minimum over all action value functions, optimizing the policy. And the policy associated to the optimal value function or the optimal action value function, we're going to call it pi star, and that's the optimal policy. And sometimes you may find this writing here, pi star smaller than or equal to pi for every pi. It means that the value function associated to pi star is smaller than or equal to the value function associated to every policy. We just write it as if we are evaluating and comparing the value of the policy, but no, what we are actually meaning is that we are comparing the value of the value function associated to that policy. It doesn't make sense to compare the outputs of the policy because that would be the action, which is typically a vector. So you cannot compare vectors. Well, you can, but it means a different thing. Okay, just here we're just stating the obvious that the optimal policy is the minimizer of the optimal action value function. So if you have the optimal action value function, you can just minimize it over the action, and the policy that you get is the optimal policy. So if we know the optimal action value function, it is trivial to compute the optimal policy. But it's very hard to know the optimal action value function, so we are not making the problem much simpler. We're just stating that these two objects are connected. And this is the very last slide, which is just stating the Bellman equations for the optimal value function and the optimal action value function. They all look the same, more or less. I think this one is very similar to the Bellman equation we have seen before for the standard value function, but here it's for the optimal value function. So the only difference is that we had to introduce this minimum in front of the right-hand side. So the optimal value function can be obtained by minimizing L plus gamma V of the next state over the choice of the control input U. So this is the Bellman optimality equation. Whereas the one before, it was just the Bellman equation for the value function without the optimality. We need to stop here because we don't have any more time. Next time, we're gonna come back to this slide to maybe digest it a bit more slowly, and then we're gonna move on talking about dynamic programming. See you on Friday.